So section 12.1 and 12.2, I combined them together. It's kind of a long one, but it's on the counting principle, permutations, and combinations. All right, all of these will be really important throughout the chapter, so you guys need to know these really well. All right, so it says much of probability has to do with counting the number of ways that certain events can occur. So for instance, suppose we wanted to know the probability of rolling a 7 with a pair of dice. So we did this in our activity. Do you guys remember the number of ways you could roll a 7? You could have 2 and 5, 5 and 2, that's different, right? 3 and 4, 4 and 3, 1 and 6, 6 and 1. So there's 6 ways. And then how many total outcomes did you guys get for a pair of dice? 36, yeah. So you have this little chart in our activity, which was a while ago. And each point in the table has X is the number rolled on your first die, and Y is the number rolled on the second die. I always think about the pair of dice being different colors. So like if I had a red one and a green one, that way you'd for sure know like 3, 4 is different than 4, 3. Does that make sense? All right, so you set up this table. So you had like 1, 6, 2, 6. I don't know why I'm doing 6. Let's do 1, 1. 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. All right, and then you said, well, what if the second number was 2? So you could have 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2. And you just keep filling in the table. So continue to fill it in. So each number on the first one is going to be 1, 2, 3, 4, 5, 6. Okay, and then the next number is 3, and then 4, and then 5. Okay, and the last row is 6. All right, that shows all the different possible outcomes you could get. Okay, so when we talked about rolling a 7, that was 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. There were 7 total ways out of the 36 possible outcomes. So it's 7 over 36 for the probability. Now this chart is nice because you can ask lots of different things. You could say, how many different ways could you get less than or equal to a 7? Or how many different ways could you get a 3? How many different ways could you get the number 2 out, right? If you add the numbers 1 and 1 make 2, there's only one way out of 36 to get a 2. Oh, 6, all right, 7. Yeah, there's only 6. Thank you, Karen. So that would be 1 out of 6. I don't know why I did that. All right, so let's go on to the next one. So it says, what is the probability of rolling less than 5? So if you add up the numbers on the die, how many different ways can you get less than 5? So let's go back to our chart and we'll look. So less than 5. Notice how I didn't say less than or equal to 5. So that means I'm going to have a 4, 3, or 2. I can't roll a 1, right? All right, so how many ways are there? 6. So that ends up being the same thing, 6 out of 36. Or 1/6. Okay, so in these last examples, it's pretty easy to list out all the ways. You know, we had 36 possible outcomes. We can easily list them with a chart. But sometimes there's so many possibilities that it's pretty impossible or very tedious to list them. So an example would be like rolling 3 dice or 4 dice. Can you imagine? Like, if you have 3 dice, that means you could have 6 possibilities for the first number, 6 possibilities for the second number, and 6 for the third number. So there would actually be 6 times 6 times 6 total possibilities. There would be 216 outcomes. So if we had 4 dice, it gets really huge, right? All right, so that's when we use what's called the fundamental counting principle. All right, so this is really important. So it says let E1 and E2 be 2 events. The first event, E1, can occur in M1 different ways. All right, after E1 has occurred, E2 can occur in M2 different ways. Then the total number of ways that the events can occur together is M1 times M2. Okay, kind of confusing. But let's say you're playing a game and you have to hit a spinner, and the spinner has 4 different outcomes: red, yellow, green, and blue. All right, kind of like a twister spinner maybe. All right, so after you do the spinner, then you're going to roll a die. All right, so there were 4 different outcomes for the first thing. So we said red, yellow, green, and blue. And then there would be 6 different outcomes for the second thing. So how many total outcomes could you have? 24. You just multiply them together. 4 times 6 makes 24. It's kind of like, do you remember the trees we did in the activity? If you created a tree, there would be 24 different outcomes in the end. All right, so number 1, it says Cold Stone Creamery has 10 different choices of ice cream, 12 different choices of toppings, and 3 different sizes of waffle bowls. If you want to get a waffle bowl, 1 kind of ice cream, and 1 topping, how many different ways can you choose your dessert? Okay, so the first, I do slots. So I say, okay, this one's going to be the type of waffle bowl. And then after I select that, I'm going to select some kind of ice cream. And then I'm going to select a topping. So how many choices do I have for the type of waffle bowl? 3. So after I choose that, I then have ice cream choices. So there's 10 different choices for ice cream. And then I want to select 1 topping. So there's 12 choices for that. So just for that scenario, right, 1 waffle bowl, 1 ice cream, 1 topping, there are 360 ways to select. So see, 3 times 10 is 30 times 12, 360. Yeah, that's a lot. I mean, I'm not even saying the different choices. When I go to Cold Stone, I get like 3 different types of ice cream and 2 different types of toppings. I'm sure you guys do too, right? So it's not even saying all those different things. This is just saying 1 ice cream, 1 topping. All right, so number 2. So true-false quiz has 5 questions. How many different sets of answers are possible? So let's say you knew nothing about the topic and you went in to take a true-false quiz. You had not studied at all, you had not paid attention in lecture, you knew nothing about it, and you just decided you were going to guess. Yikes. Please don't do that in Algebra 2. So if you have 5 questions, how many choices do you have on each question? 2. So that means you have question 1, question 2, question 3, question 4, and question 5. And for each question, you have 2 choices. So I could pick true or false for the first one. After I select that, I have true or false for the next one, true or false for the third, true or false for the fourth, and true or false for the 5th. So 2 choices for each one. So you end up getting 2 times 2 times 2 times 2 times 2, or 2 to the 5th, which is 32. So if we then go on and say, well, what's the probability that you would get 100%? There's only one way to get 100%, right? There's 32 different outcomes for that small little quiz. So your probability of getting 100% would be 1 out of 32, which is 3%. So please don't just guess on things like that. All right, so number 3. So a multiple choice quiz has 7 questions with 4 possible answer choices, so A, B, C, or D. So how many different sets of answers are possible? All right, so if we have 7 questions, that means I have 7 blanks. So those are the questions. And each one has 4 choices. Okay, so that ends up being 4 times itself 7 times, so 4 to the 7th. So 16,384 different sets of answers. Yeah, so if you guess on that one, the probability of you getting 100% is 6.10 times 10 to the negative 5th. Pretty much 0%. You're not going to get 100%. But But luckily, you know, you guys study for exams, you've attended lectures and things, so you would have a better probability. You're not just guessing, hopefully. Sometimes. All right, number 4. So an exam has 10 multiple choice questions and 5 true-false questions. So how many different sets of answers are possible? Okay, so think about your blanks. So if you had 10 multiple choice questions, you'd have 10 blanks to start out with. And let's say they're A, B, C, D, and E again. Oh no, A, B, C, and D again. Forgot to say that. And 5 true-false questions. So the first 10 slots are going to be what number? 4. So we're going to say 4 to the 10th. And the next 5 slots are going to be 2s, right? So it's going to be 4 to the 10th times 2 to the 5th. So we do 4 to the 10th times 2 to the 5th. So you get 3, 3, 5, 5, 4, 4, 3, 2. So 33,554,432.
It's probably a good chance.
Yeah. You're going to ace it. Yeah, that's why I always hate multiple choice tests, because my students always do bad because you don't get any partial credit or anything, you know, so if you like mess up a little bit, you're going to get it wrong. I don't know. I don't like multiple choice tests. All right, so yeah, Sarah, do you have a question?
Oh, no, I just said just
She likes multiple choice. All right, so I don't know if you guys remember, like way back in the day, Mr. Sarek and I were talking about this the other day. Indiana license plates all used to look the same. So now you have like all these different choices for license plates, which I think is cool that you have these different choices. But they all used to look the same. And the first 2 numbers used to be your county number. So I was from Delaware County. So that was the 18th county listed in alphabetical order. So all of our license plates started with 18. And it was kind of fun because then you'd be like, oh, they're from my county. Do I know them? You know, like you'd be like, ooh, hey. Or you could try to guess where people are from. Like, what's county 2? Oh, it's Adams. You know, it's very nerdy. Anyway, so, you know, these license plates used to happen. So in 2007, a Marion County license plate began with the number 49 and then had a letter followed by 4 other numbers. Okay, so that means that the first 2 spots have already been chosen. They are already 4 and 9. There's only one choice for those numbers. You only are putting in 4, you're only putting in 9. So usually if those are already a number, I'll just kind of put that number in there. Okay, and then it had a letter followed by 4 other numbers. The letter could be any letter in the alphabet, and the numbers could be any digit 0 through 9. So how many choices do I have for the letter? 26, right? And the numbers 0 through 9. 9 numbers? 10 numbers, right? Because you have 0 as well. So 10. And they can repeat, right? If I had the number 1 in there once, it can be in there another time. So 10, 10, and 10. So we'd have 26 times 10 times 10 times 10 times 10. Well, we know when we multiply by 10, we add zeros. So I have 1 0, 2 0, 3 0, 4 zeros. So 260,000. Okay, it then goes on to say, do you think this is an adequate number of plates? The approximate population of Indianapolis at that time was 782,000. So is that enough? No. So what Indianapolis did, like most counties it worked for, you know, Delaware County was fine, that was plenty. But what Indianapolis had to do was they used 49, then they used 99, 98, 97, 96, and they kept going down until they had enough license plates. So pretty crazy. Yeah, do you guys know how many counties there are in Indiana? I feel like I should know this. I need to look it up. I think it's 86. All right, it's definitely not 99 though. All right, so the next one. So it says an ID code consists of 2 of the digits 1 through 5, followed by 3 letters A, B, C, and D. So an ID code could be something like you use to get into a building or something, you know, like a PIN. All right, so we have 2 digits 1 through 5, and then 3 letters A, B, C, and D. It says you're allowed to repeat numbers and letters. So for instance, you could have 22, ABC, or you could have 12, AAB. Those are both allowed. So how many different ID codes are possible? So what do you guys think? What goes in the first blank? 5, right? 5 numbers there. 5 numbers here. 4 choices for each of the other ones. You end up with 1,600 possibilities. Okay, so that'd be pretty good for, a company that's pretty small. Like, people would have different ID codes. But sometimes ID codes are really not good. They're easily breakable. I mean, can you imagine if you had 1,600 employees and they each had an ID code? You could just put whatever you want into the system and then get into the building, right? Doesn't really make any sense. All right, so sometimes you really need to think about how many different ID codes you have. I remember when we were in college, one of my good friends, she was trying to get into her sorority house and she couldn't remember the ID code. And I was like, well, I mean, do you remember any of the numbers? She's like, I remember, like that it starts with a 2 and I don't know, I think there's a 4 in there and there were like 4 different 4 numbers. And I figured it out on like the second try. I was like, this isn't a very secure system. Like, there aren't many outcomes on this. But she was laughing. She was like, wow, that was pretty quick. All right, so number 7. So repeat example 6, but now make the additional stipulation that you cannot repeat numbers and you cannot repeat letters. So how many codes are possible now? Okay, so that means we have the 2 numbers to start out with, and then we have 3 letters. Oops, A through D. And we can't repeat. Okay, so for the first number, I have 5 choices. I have 1, 2, 3, 4, and 5. Okay, it doesn't matter what you pick. So let's say Taylor's figuring out this code and she picks 3. She knows that first number is 3. So she goes ahead and puts in 3. How many choices are left for the second number? 4. Do you see how that works? So after you select the first number, there's now only 4 choices left. Okay, same with the letters. So how many choices do I have to begin with for the letters? 4. But once I select one of the letters, so let's say I pick B, I only have A, C, and D left. So I have 3 choices. Now if I select another letter from that list, like D, now I just have A and C left. So 2. Does that make sense? Okay, so we're going to have 5 times 4 times 4 times 3 times 2. So we get 480. All right, let's try this one. So repeat example 6, but now make the additional stipulation that you cannot repeat letters, but you can repeat numbers. How many different codes are possible now? So still we have 1 through 5 for the first 2 numbers, A through D for the 3 letters. Okay, you can't repeat letters though. You can repeat numbers. So if I can repeat numbers, that means I have 5 choices for the first slot. How many choices for the next one? 5, because I can still pick whatever number I'd already picked. Okay, but now I can't repeat letters, so once I pick one of those letters, so A through D, so I have 4 different choices. Let's say I pick C, then there's A, B, and D left for the next one. Let's say I pick D, so there's only 2 choices left, right? So 5 times 5 times 4 times 3 times 2. So 600 choices. Okay, is that all making sense, the fundamental counting principle? I think most people like that. I always call it the slot method. All right, so permutations and combinations are a little bit more confusing, but they're not too bad. So there is a difference between them. So permutations, it says if R items are chosen in order without replacement from n possible items. Okay, so the key word in this is in order. So order matters. The number of permutations, we write it a couple different ways. You might see Pn comma R, or you might see NPR, like that. It equals n factorial over n minus r factorial. Okay, so we'll talk about that in a second. For permutations, you can still use what we call the slot method. For combinations, you cannot. All right, combinations, it says if R items are chosen in any order without replacement from n possible items, and they're not in a particular order, the number of combinations is, so we write this a couple different ways. We say CNR, or we write NCR, or we sometimes write N over R like a fraction. R is kind of funny. Like that in parentheses. Remember seeing that before? I talked about Pascal's triangle. And what that ends up being is n factorial over r factorial times n minus r factorial. Okay, these buttons are on your calculator, so don't freak out. Okay, then I said in permutations, the order matters. Permutations can still be found with the slot method we used before. So only on the permutations can use the slot method. Okay, so let's talk about this. So number one says, how many different ways can we arrange the letters X, Y, and Z? Notice how I use the word arrange. Does that make you think that the order matters or the order doesn't matter? So is X, Y, Z the same as Z, Y, X? No, because we're talking about how many different ways we can put them in a certain order, right? So for this, order matters. So X, Y, Z is different from Z, Y, X. So you guys are probably like, well, when are they not? They're always different, right? The ways that they will be the same is if you have like a committee. So let's say I have, I need 5 students for a committee where you're going to help with Community Day, all right? And I have all of you to select from, but I'm only going to choose 5. So is the group Andrew, Taylor, Kern, Melvin, Allie, is that the same as Allie, Melvin, Kern, Taylor, Andrew? Yeah, you guys are all just in a committee. You don't have specific titles or anything. You're all just grouped together. Okay, that's going to be a combination. Okay, permutations, the order matters though. It's like, you know, putting things in order on a bookshelf or something like that. Like if you want things in alphabetical order or things like that. So order matters for permutations. Okay, so how many different ways can we arrange the 3 letters then? So we have 3 letters, and we want to arrange all 3 of them. So it ends up being P 3, 3. So you have n items, you're arranging them in n different locations, 3 different locations. So let's try it with our formula. So I'd have 3 factorial over 3 minus 3 factorial, which is 3 factorial over 0 factorial. What was 0 factorial? 1. 3 factorial was 3 times 2 times 1. So you get 6. So that's the first way. Now I said with permutations you could also use slots. So basically you have 3 slots. You have 3 choices for the first one. After you select that first position, you have 2 choices and then 1 choice. So you get 6. Much easier with the slots, right? So what if you have X, Y, Z, and W? So this was just X, Y, and Z. So what if I have X, Y, Z, and W. How many choices would there be for that? You'd have 4, 3, 2, and then 1, right? Multiply them all together, you get 24. So there'd be 24 different ways to arrange those in order. So basically you'd have X, Y, Z, W, X, Y, W, Z, X, Z, W, Y. You have to go through all those different possibilities. All right, number 2, 6 fifth grade students are competing in a spelling bee. How many different ways can they place? So when you see the word place, does the order matter or does the order not matter? Order matters, right? So if order matters, that's the permutation. It's easiest just to use slot method in that case. You can use the factorials and everything, but I would just say, okay, well I have first place, second place, and so on, third, fourth, fifth, and sixth. How many students could possibly get first place? 6 of them. Once first place is selected, there's only 5 left for second place. Then 4, 3, 2, 1. Kind of works better the other way, right? If you actually think about a spelling bee. Like 6 people could possibly get 6. Once that 6th place person is determined, so once the first person's out, there's 5 people left for 5th place, and so on. Okay, so 6 times 5 times 4 times 3 times 2 times 1 ends up being 720. Notice that's just 6 factorial. That was because it was 6 factorial over 6 minus 6 factorial. 6 factorial over 0 factorial. All right, Charlotte was given 8 choices in her art class for an assignment. She has to choose 3 of them. All of them are going to be due on Friday. How many different ways can this be accomplished? So what do you think about this one? Yeah. Why not, Sarah?
Because it's just having different ways.
Yeah, and they're all due on the same day, right? So I don't think Mrs. Barger cares if you turn in one before the other. You're just turning in a group of 3 all at once, right? So order doesn't matter. Okay, so order doesn't matter. We had a group of 3 things, all due at one time. Okay, so that means that we have 8 possibilities to select from, and we're supposed to select 3 of them. All right, so that's the C8-3. You could write that lots of different ways. Remember, you could say 8C3, or you could say 8 over 3 like that. Doesn't matter. Pick a way that you like. Which way do you guys prefer? The first one? Okay. All right, so if I'm using the formula, it's going to be 8 factorial over r factorial, and then 8 minus r, or sorry, n minus r factorial. So n factorial over r factorial times n minus r factorial. We find it, so I do 8 times 7 times 6 times 5 factorial. Why did I stop at 5 factorial? Because you have 5 factorial on the bottom, right? That's 5 factorial. And then we have 3 factorial, 3 times 2 times 1. So 5 factorial goes away on top and bottom. 3 and 2 make 6, so you end up with 8 times 7. So 56 is your answer. All right, I told you you would be able to use a calculator. Do you guys remember how we did this with Pascal's triangle? Did we do this? Maybe we didn't do this in this class. All right, so you're going to hit, we want 8, choose 3. So hit 8 first. Then you're going to hit math. You're going to arrow over to PRB. You go down to NCR. and then you hit 3. See how you get 56? So that's doing 8, choose 3. Combinations, I would say choose. 8, choose 3. All right, number 4, 15 students are interested in an upcoming community service event, but Mr. Morrison only has room for 6 more students. I'm sure that would never happen. I'm sure he would take all of you on the bus. So in how many different ways can he choose these students? Okay, does the order matter? No. Right, he has 15 students. He's going to select 6 of them. So we're going to do 15, math, PRB, NCR, 6. You get 5,005. Yeah, hit. Oh, sorry. So hit math, go over to PRB, and then down to NCR.
The second one's
And then it's 4. Oh wait, 6. 15, choose 6. All right, so let's try the next ones. So there's lots of these. So there are 12 countries competing for the Olympics in team gymnastics. How many different ways can the gold, silver, and bronze medals be awarded? Order matter, order doesn't matter? It doesn't matter? It matters, right? You don't want to get bronze when you really should have gotten gold. All right, this is like one of those things where you have like placement, right? Places matter. Okay, so order matters. You don't always have to write this on your homework. I'm just writing it so you guys have it for your notes. All right, so you have 12 countries. How many different places do we have? 3. Since order matters, this is a permutation. Permutation, think places. Combinations, think committees, right? Places, committees. All right. You can use the formula, which is easy. It's just 12 factorial over 12 minus 3 factorial. So that's 12 factorial over 9 factorial. So you're going to have 12 times 11 times 10 times 9 factorial, and that's going to cancel with the 9 factorial on the bottom. So 12 times 11 is 132 times 10, so you get 1320. Now remember I told you with the places, so permutations, you could also use the SOT method, right? So think about how you would do this with the SOT method. What would you do? There's first, second, and third, gold, silver, bronze. 12 times 11 times 10. That's it. Same thing. All right, number 6. So a local bank allows debit card codes to be made from the numbers 0 through 9. None of the numbers are allowed to be repeated in order to prevent theft. How many different codes are possible? So they don't want you to have like 4444. Oh, that's a really hard code. Pretty sure someone could guess that one. All right, so they don't let you repeat them. I think they let you repeat a couple. I'm not sure. So you have 4 numbers, 0 through 9. How many choices for the first spot? 10. After you select the number, you have 9, 8, 7. Is this a permutation or is this a combination? Permutation, right? The order matters. The code 1, 2, 3, 4 is not the same as 4, 3, 2, 1. So order matters. So if you did 10 numbers, you're selecting 4 of them, ordering 4 of them, you'll get it. So 10. Notice how you have NPR on your calculator as well. Both of these end up being 50-40. Either way you do it. The last 2. Yes, it does. So NPR is permutations, NCR is combinations. All right, think about which one number is usually going to be, well, which number is going to be bigger. So a permutation or a combination. So let's say I had 3 books and I was trying to arrange them. That'd be a permutation if I'm trying to put them in a certain order, right? All right, so that would be 6, 3, 2, 1. You'd have 6 ways to arrange them. What if I just had 3 books and I just wanted to select 3 books? Only one way to select 3 books, right? So you can think of different scenarios like that. Like if I had 5 students and I wanted to order 3 of them, put them in order, you'd have 5 times 4 times 3. All right, but if I just wanted to select a group of them, there's a lot less for the possibilities. So you can try to think of different things. All right, so a school is selecting student council officers. There are 7 students running for office. So the office positions are president, vice president, secretary, treasurer. How many different ways can the school select officers? So we don't do this here, but. So let's say we have president, vice president, secretary, and treasurer. There are 7 students running for these office positions. So I have 7 choices for the first one. After I choose the president, I get 6, 5, 4. Why did I decide that order mattered on this one? Yeah?
You know, if you're running for president, if you want to be president, you're not going to be okay with anything.
Yeah, you wouldn't want to be in the secretary spot if you're running for president, right? So order matters. It depends on which slot they're going into. All right, so I get 7 times 6 times 5 times 4. 840. All right, we'll go ahead and pause so you guys can go on break. All right, so let's continue. So number 8 says, this is a little bit different. So let's think about how this is different than before. So it says, again, if Cold Stone Creamery has 10 different choices of ice cream, 12 different choices of toppings, and 3 different sizes of waffle bowls, how many ways can you create a dessert with 1 waffle bowl, 2 types of ice cream, and 2 types of dessert? Or dessert. I don't know what I'm saying here. 2 types of toppings. Okay, so we're going to select waffle bowl. All right, now here's the tricky part. 2 types of toppings. Does it matter what order you put the toppings on? No, you could do sprinkles first and then chocolate syrup. I mean, it's all getting mixed up in your belly anyway, right? Doesn't matter. All right, guys, no, we didn't. I'm explaining the difference. So what is the difference? So order doesn't matter on those toppings, does it? So on the toppings, it has to be a combination. Okay, but then once we pick the toppings, well, I guess for ice cream or toppings, so combinations for these. So let's say we have the ice cream first. So how many different choices of ice cream did I have? 10, and I wanted 2 types of it. So I have 10 choose 2 for this spot. Does that make sense? Why you do that? So you have C, 10 choose 2. All right, but then once I pick the ice cream, then I'm going to do the toppings. How many choices for toppings did I have? 12. How many am I going to select? 2. So that's 12 choose 2. For waffle bowl, there's still only 3 choices for waffle bowl. So you're going to take 3, you're going to multiply by C, 10 choose 2, and then you're going to multiply by 12 choose 2. So let's find out what 10 choose 2 is. So do 10, math, arrow over to PRB, go down to NCR, 2. You get 45. So I have 3 times 45 times. Now, you can do a shortcut. You don't always have to go back to get NCR. So if you do second enter, that pulls up the last thing you put in. So you can now change the 10 to 12, right? You get 66. So 3 times 45 times 66 is 8,910. How about we just try all those different combinations for the rest of the time for Algebra 2? You know, each day we'll just eat mounds and mounds of ice cream.
Yes.
Yeah. All right, next up. So suppose Taylor has 8 pairs of pants, 10 shirts, 7 sweaters. She's packing for a weekend trip to Colorado and needs 2 pairs of pants, 4 shirts, and 3 sweaters. How many ways can she do this? Okay, so we're going to need pants, shirts, sweaters. All right, so how many choices for pants do I have? 8. How many am I going to select? 2. So I'm going to have 8 choose 2. Shirts. I have 10 shirts. I'm going to select 4 of them. 10 choose 4. And sweaters. She has 7. She's going to select 3 of them. So 7 choose 3. So let's find each of these numbers. So let's do 8, math, arrow over to PRB, down to NCR, 2. There's 28 for the first one. All right, let's do 10. So you might have to insert 4. Do 10. Are you guys doing second enter to pull that back up? Okay, so now do second enter. So now we want 7, so then delete out the 0. 3. A lot of outfits. So 205,800 different ways to select these. So I feel like that's not a very extensive wardrobe. 8 pairs of pants, 10 shirts, 7 sweaters, but lots of different possibilities for outfits.
It's like when you watch What Not to Wear, and you're like, oh, they just took away our entire wardrobe
Yeah,
and
I
gave her
hate
like
that.
10 pieces of clothing.
Yeah, so Gabby said when you guys watch What Not to Wear, have you guys ever seen that? And they like take away their whole wardrobe and throw it away, and then they buy them like 3 things. All right, so number 10. So there's 7 girls and boys and invisible children. From this group of students, a committee of 4 will be chosen to go to Uganda. How many different ways can a committee be formed that contains at least 3 women or girls?
Ladies.
All right, so we want at least 3 women. So that means we could have, if there's 4, a committee of 4, that means we could have 3 girls and 1 boy. Or we could have all 4 girls, right? So we need to find the number of ways for both of those outcomes. Does that make sense? Those are all the possible outcomes. So 3 girls and 1 boy. All right, so how many ways can I do this? So we're going to do 1 blank for the girls, 1 for the boy. How many girls did I have? 7. The order doesn't matter. I don't care which order they're selected. I'm just caring that I'm getting a group of students, right? So we're going to take those 7 girls and we're going to select 3 of them. So 7, choose 3. And then for the boys, I have 6 boys. I'm going to select 1 of them. We're going to multiply together. 7, choose 3, we just did in the last one. I still see it on my screen. I get 35. 6, choose 1, ends up being 6. You have 6 boys, you're going to choose 1 of them. There's only 1 way to choose 1 of the boys, or there's only 6 ways to choose 1 of them. So you get 210. Okay, now we do the all 4 girls. So now we just have 1 slot, right? They're all girls. We had 7, we're going to select 4 girls. 7 choose 3 and 7 choose 4 end up being the exact same thing. Isn't that weird? You guys can try it. You'll get 35. The reason is because these combinations actually come from your Pascal's triangle. If I use this row, this is 3 choose 0. This next one's 3 choose 1. The next one's 3 choose 2. And the last one's 3 choose 3. So it's symmetric, right? So if the numbers add up to be the original number 3, then they're going to be the same thing. Kind of weird. All right, you could also think about the formula. If you think about that, like if I had 7 choose 3, that's 7 factorial over 3 factorial times 7 minus 3 factorial. So that's just 7 factorial over 3 factorial times 4 factorial. And 7 choose 4 would be the exact same thing because it would be 7 factorial over 4 factorial times 3 factorial. Same thing. Okay, anyway, so you get 35. So your total, oops. How many different ways can the committee be formed? Well, there are 210 ways to have 3 girls and 1 boy, and there's 35 ways to have 4 girls. Do I multiply them? Do I add them? Do I divide them? What do I do? Add them, right? So you do 210 plus 35, so you get 245. So 245 ways to select the committee. Okay, and the last thing we're going to talk about are ways to arrange words. Okay, so when you see the word picture, all of the letters are different. None of them are repeated, right? So if you're talking about all these different letters, we have how many letters? 7 letters, right? And they're all different. I might use the word distinct. No, distinct means they're all different. All right, so this is just like books on a bookshelf. If I have 7 books and I'm going to rearrange them, order matters, right? So you're going to get P7, 7 items that you're rearranging in 7 different slots. You could also do your slot method. 7 times 6 times 5 times 4 times 3 times 2 times 1. So basically it's just 7 factorial. So you get 50, 40. Now let's try the next one. So how many ways can you distinctly rearrange the letters in the word bookkeeper? This is the only word in the English language that has 3 double letters like that, O-O-K-K-E. All right, so this one's a little bit different because now when you're rearranging the letters, some of these like words that you're creating, they're not really words. But some of these some of these orders that you're creating are the same as other ones, right? Because like you have 2 O's, you have 2 E's. No, you have more than 2 E's, you have 3 E's. So when you're rearranging them, you could get repeats, basically. So you need to divide by the number of times that you've repeated. So it's a little tricky. So how many letters do I have in all? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 letters. So based on that last example, we said there were 7 factorial ways to rearrange 7 letters. So we have 10 factorial, but like I said, some of them are repeated. So if you have like O in there, the O's could be in the same spots in some of your words. All right, so what you need to do when this happens is you need to talk about the number of things that are repeated. So we have 2 O's, we have 2 K's, and we have 3 E's. Do we have anything else? No. Okay, so when you have those repeats, you divide by them. So you divide by 2 factorial, 2 factorial, 3 factorial. Okay, basically, 3 factorial is 6. Like there's 6 different repeats for the e's. I don't know, like 6 factorial ways to rearrange those 3 e's in the same positions. All right, so we figured that out. So make sure when you put this into your calculator, remember do 10 factorial divided by and then put parentheses around the whole denominator. Some of these you can do in your head, I'm sure. Like 2 factorial is 2. All right, you end up with 151200. All right, so I want you to try the other things on this page. So notice how these are all like factorial questions, combination questions. These are all like basically calculator questions. So go ahead and try them, and then I'll put the answers up here. So number 12, how many ways can you rearrange the word letters in the word mathematics? So think about how many total letters you have, how many repeats, and so on. And I'll put the answers up here in a second. Okay, so on the first one you should get 4,989,600. Did you guys all get that? So you had 11 letters, 2 M's, 2 A's, 2 T's. So divided by 2 factorial, 2 factorial, 2 factorial. All right, the next one, 5 factorial you should find is 120. 2 factorial is 2. 120 plus 2 is 122. Notice that's not the same as 5 plus 2 in parentheses factorial. You can't like distribute a factorial in. So 5 plus 2 factorial is 7 factorial, which is 5040. And then P 6, 2, so 6 permute 2, ends up being 30. Okay, now the next one, say without a calculator. So your formula for permutations is n factorial over n minus r factorial, so put that on there for you. So n is your first number, r is the second number. So we have 4 factorial over 4 minus 3 factorial, which ends up being 1 factorial, which is 1. So you get 4 factorial over 1 factorial. So you get 4 times 3 times 2 times 1, which is 24. Okay, the next one. Combinations looks almost like permutations, but you have an extra r factorial that you're dividing by. Okay. So on this one we have 4 factorial over 2 factorial. 4 minus 2 factorial ends up being another 2 factorial. Don't think that since 2 times 2 make 4 that everything cancels. It doesn't, right? So 4 factorial is 24. You divide by 2 times 2, right? 2 times 1, 2 times 1. So divide by 4, you get 6. Run out of room. All right, 5 choose 3. So it's going to be 5 factorial over 3 factorial, 2 factorial, right? 5 minus 3 factorial. So think 5 times 4 times 3 factorial. You have 3 factorial on the bottom, and then you have 2 and 1. So I wrote that because the 3 factorial was going to cancel like that. So you have 20 over 2, which is 10. The next one, you have 10 factorial over 8 factorial. So you get 10 times 9 times 8 factorial. It's going to cancel with the other 8 factorial. So you get 90. The next one, you have 4 factorial on the top, but you have 5 factorial on the bottom. So we're going to do 5 times 4 factorial, and then 4 factorial on top. Then I have 10 factorial on top and 9 factorial on the bottom. So think of 10 times 9 factorial over 9 factorial. So the 9 factorials cancel, the 4 factorials cancel. So see how you get 2? How did I get the 4 on the bottom? Because you have 5 factorial, and I knew 4 factorial was above it. All right. So in many ways, this is faster than doing it on your calculator, right? And there's a lot of errors you can make on your calculator. You could forget parentheses on the top, forget parentheses on the bottom. All right, and then 8 permute 2 is 8 factorial over 8 minus 2 factorial. Basically what that's saying is you have 8 numbers and 2 slots. So you get 8 factorial over 6 factorial. So it's 8 times 7 times 6 factorial over 6 factorial. 6 factorials cancel, you get 56. See how that's 8 numbers with only 2 slots? It's like getting first and second place. 8 people can go in the first spot. 7 people can go in the second spot. Okay. All right, that's it.